All right, so far we have disjoint union, Cartesian product, some basic building blocks, and the sequence construction. So now let's look at a few fundamental examples of these constructions. So the first one will be to uh, start with an atomic class. So I'll just write it as this curly Z, which it will be just a dot in set brackets. And so this is just an atomic class, and if I take the sequence construction of that atomic class, I'll get a neutral class followed by my atomic class, followed by the Cartesian product, which would just be this single ordered pair, and then I'd have this single triple of 3 dots, and so this is actually isomorphic to the non-negative integers because there's one element of size 0, one element of size 1, one element of size 2, one element of size 3, and then the ordinary generating function for this combinatorial class will just be 1 plus z squared all the way down, which is just the familiar geometric series. So that's simple enough. Let's look at a slightly more complicated example. Let's take an atomic class, Z, and the product of Z with itself to give us just an element of size 2, which we write it in this funny way just to keep track of things a little better. Because when we do a sequence of sequences, we don't re-bracket things. So you have to be a little careful here and understand what we get out of this example. So the sequences formed from dot and these 2 dots. So again, this would be an element of size 2, and the dot has just size 1. Well, I have the empty sequence. I have so maybe I should sort of put it in brackets, just the sequence of 1 dot. And then I would have sequences of size 2, so that could be these 2 dots, followed by the other sequence of size 2 is just the 1 element. This dot's connected by a line. So there is some subtlety here. You'd have to separate between, if we used completely traditional notation here, this would be the set containing these 2 dots. And so it would get a little confusing when I form sequences of size 2. So the sequences of size 2 would be to take dot comma dot. That's not too bad, but then here you'd have the sequence of one of these elements. So that's why it's kind of convenient to use a separate notation so we don't get too hung up on the parentheses. And then the sequences of size 3 would be dot, 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 2 dots connected in 1 dot, or a dot and a bar. And there are 3 of these. But luckily, we can just read off the ordinary generating function for this combinatorial class. So it's just, I would take the ordinary generating function for z plus z cross z. So this has ordinary generating function z plus z squared. And you apply the sequence construction to that, and you just get 1 over 1 minus z plus z squared. And you get this power series here. And let's see let's see if we recognize these numbers. Well, we start out with 1 element of size 0, 1 of size 1, 2 of size 2, 3 of size 3, And then how do you generate ones beyond that? Well, we can think of this recursively. And so if I have things of size n plus 1, well, anything in here will be the sequence of dots and bars, where a bar has size 2. And so anything in here will either end with a dot or end with a bar. So if it ends with a dot, it'll be an element of an, comma, some dot. Or it'll be an element of a n minus 1 followed by one of these bars. And so this gives us actually the recursive formula that a n plus 1 will be equal to a n plus a n minus 1. And this is the same recursion formula that the Fibonacci sequence satisfies. And so you'd see that the numbers here actually end up being the Fibonacci sequence, which goes 1, 1, 2, 3, 5, 8, 13, and so on. And so the Fibonacci numbers are exactly encoded by this very basic sequence construction. Let's look at one more simple example. Let's take A and B will be distinct things of size 1. So these are distinct atomic classes. And then if I take the sequence construction of this disjoint union, well, what is this going to be? Well, I take sequences formed using A's and B's, so it'll be just binary words formed using A and B. I mean, I could have used 0 and 1. But the ordinary generating function is what we saw earlier for binary words, which is 1 over 1 minus 2z. And the reason is that the ordinary generating function of this combinatorial class, well, I have this disjoint union, I actually have two elements of size 1, and that's it. So the ordinary generating function is 2z. And so when I form a sequence of these, my generating function is just 1 over 1 minus 2z. So these are these sort of very fundamental examples that come from sequence, but it's important to study these to capture some of the subtleties of the notion. In the next video, we will look at more complicated constructions involving sequence and related to compositions of integers.